Okay, so we are doing 2.3 product and quotient rules and higher order derivatives. So the first thing we're going to talk about is the product rule. And the product rule has this really big, fancy definition. Key things to notice is that the product of two differentiable functions, so f and g by themselves have to be differentiable, then their product is differentiable. And so what you notice is this is my first function and this is my second function. And it is the first function times the derivative of the second function plus the second function times the derivative of the first. When I was in high school, my teacher taught me 1d2 plus 2d1, where the d is representing the derivative. So it's the first times the derivative of the second plus the second times the derivative of the first. So we'll do a couple of practice problems. Okay, so we're going to find the derivative of 3x minus 2x squared times 5 plus 4x. So this is my first function, and this is my second function. So I'm going to use the rule 1d2 plus 2d1, or the first function times the derivative of the second plus the second times the derivative of the first. So this is not equal to, all right, the first derivative is equal to the first function times the derivative of the second function plus the second function times the derivative of the first function. Keep in mind those derivative rules were we learned in previous section. Keep those going. We need to simplify. So we'll have 12x minus 8x squared, and then we'll have to FOIL this. So 15 minus 20x minus 12x minus 16x squared, and then combine your like terms and we'll get negative 24x squared plus 4x plus 15. Next one, the product looks littler, but we have these two things. Okay, so x and e to the x as our two things. So I will y prime. I will have my first, the derivative of e to the x is e to the x, so 1d2 plus the second 2d1. And you don't have to write that one. You can leave it. But one thing, it does look a little better, and in the future we will have to factor things out. So it's kind of a good habit to go ahead and get into it. But it is correct the other way too. Last one, this is not a product. The second thing, the 2 sine x is, but this is a product. So we'll do the product rule on this, but we'll just do regular on the other. And so I will use a different notation this time. And I will have my first function times the derivative of my second function plus my second function times the derivative of my first function. And then I still have to derive this part. So minus 2 cosine x. The only real simplification, well, you can, if you notice this is 2 cosine x's and this is negative 2 cosine x's, you can get rid of those. And you don't want to leave this negative in the middle, so you should rewrite it like that. So then if we have a product rule, we also have a quotient rule. And so again, they have to be differentiable, and your g function, since it's in the denominator, can't be 0. So what it is, it's your denominator times the derivative of your numerator minus your numerator times the derivative of your denominator, all divided by your denominator squared, as long as, again, g is not 0. What we learned is low d high minus high d low all over the square of what's below. Okay, low being the denominator, high being, and it has a rhymey thing, and so that's why I do it. So low d high minus high d low all over the square of what's below. Okay, so we have this. What I would do first, we're going to write the equation with tangent lines. So remember, tangent line, the slope is the derivative. So in order to write the line, we need the slope first. So we'll calculate our slope, which will be f prime of x. But I would also consider rewriting this, because if you notice we have a quotient and a quotient, I would change this to x to negative 1 instead of 1 over x. So we'll do the quotient rule. I'll do low d high, derivative of the top. Okay, well, derivative of 3 is 0. The derivative of x to the negative 1 is negative x to the negative 2. So low d high minus high d low, and the derivative of the bottom is just 1. And you don't have to write that 1, but you can. All over the square of what's below. And then we can simplify this carefully. All right, and if we simplify this, we are going to get, I would just actually rewrite it where it'll be easier. You're just going to plug in numbers. So it would probably simplify, but it's just as easy to plug numbers in here. So you're going to do at x equals -1. So go plug in -1 everywhere there's an x so that your slope is equal to 0. So then I'm going to use y minus y equals mx minus x, and I'm going to write the equation of my tangent line. Okay, so I'm going to do y minus the y value they gave me in the ordered pair equal to my slope times x minus my x value they gave me in ordered pair. And you can leave it like this, or you can leave it like this as you simplify, or you can leave it like that. And I'd be aware of all of them because AP test is multiple choice and it can show up in any form. Oh, well, here we go. Here's another quotient. So dy over dx for our derivative. We're going to do low, derivative of the top, d high, minus high, so it stays the same, d low, derivative of the bottom, all over the square of what's below. So we need to distribute in the top. And I'm not going to FOIL at the bottom. Sometimes you'll need to, sometimes you'll not. But let's just see how the top simplifies before we do that. So we'll have -5x squared and a positive 4x, a 5. And that won't be factor. Well, you could check it. But we'll be able to get it like that. And that's it. That would be our quotient. So then we have these quotients, but we don't have to do them as quotients. You can actually just rewrite them. So I can actually write this as, instead of dividing by 6 here, I can actually divide each part by 6 or multiply each part by 1/6 because that's the same thing as dividing by 6. So I'm going to have 1/6x squared plus 3 over 6 is 1/2 x. So then I can take my derivative and I will get 1/3 x plus 1/2. This concept, just think of this as your coefficient, so 5/8 x to the 4th, so that when I do my y prime, I'll multiply 4 times 5, which is 20 and over 8, or the 4 and the 8 will simplify to 1/2. Either way, when you simplify that multiplication, you'll get 5/2 x cubed. All right, this one, what I would do is, it probably would be easier to go ahead and distribute that -3 through. If you notice, all parts have an x, so I can actually cancel out this x with one of those x's, leaving me with -9 plus 6x all over 7. And just like the one earlier, part A, where we gave each one the 7, the derivative of, if I do dy over dx, the derivative of -9/7 is 0, so I'm not going to write it, and the derivative of 6/7 x is just going to be 6/7. Okay. And then this last one I would rewrite 2 to 9/5, but instead of the x in the denominator, I would pull it out to the numerator technically and give it a power of -2, so that when I do my derivative, I get -18/5 x to the -3, and you should rewrite that to -18/5 x cubed, keeping those exponents positive. These you just need to memorize. Shortcuts for memorizing or little clues is if it has a tangent, cotangent, or regular, it's going to have a squared, and it's going to be some version of secant. If you have secant or cosecant, it's going to have two terms being multiplied together. If it has co in it at all, cotangent, cosecant, cosine, its derivative has a negative. So you kind of figure out ways to help you memorize it, but you have to memorize those. So we're going to differentiate these. A little hard to read. Y equals x minus tangent x. Okay, and so if we're doing that, okay, the derivative, hold on, my computer is being weird. Okay, so we know the derivative of tangent is secant squared x. So if we're doing the derivative dy over dx, it's going to be the derivative of x first, which is just 1, minus the derivative of tangent x, which is just secant squared x. Okay, and then if you notice, part B is a product. Since it's a product, we'll have to do the product rule. So this will be my 1, this will be my 2. And so my y prime is going to be 1 d2, and the derivative of secant is secant x tangent x. Okay, 1 d2 plus 2 d1, and the derivative of x is just 1, so I'm not going to write it. What you can do from there, if you notice they both have a secant x, it would be simpler if you would factor out a secant x, leaving you with x tangent x plus 1. Okay, we're going to differentiate both forms of this. So this is an identity for each one. If we do the left, it should be equal to the right. So we will just do the left side derivative and we'll do the right side derivative, and we should end up with the same thing. And so on the left side, when I do this derivative, I will have to do the quotient rule. So I will do low d high, the derivative of 1 is 0, so I won't write it. The derivative of cosine is negative sign, but it already has a negative, so it's going to be positive sine. So low d high minus high d low, and the derivative of sine is cosine x. Okay, just like that. And I can simplify the top. Oh, all over the square, what's below? And the top is sine squared x minus cosine x plus cosine squared x. Okay, so that I have this. And an identity from all over, sine squared up, let's forget that. Identity from trig says that if I have sine squared plus cosine squared, it's equal to 1. If you notice, I do have that in these two. So I'm going to have 1 minus cosine x all over sine squared x. Okay, that would be that derivative. We'll go do this other one. Okay, so the other one, dy over dx. Okay, the derivative of cosecant, if you recall, is going to be negative cosecant x, cotangent x, and the derivative of cotangent is negative cosecant, so it's going to make it a plus. I'll left off to C. And we can actually prove that these are the same by, I mean, those are the derivatives, and it doesn't look like you can simplify it much, but you really can, because I can rewrite this as negative 1. Cosecant is 1 over sine, and cotangent is cosine over sine, and cosecant is 1 over sine, but since it's squared, it's still squared. So I have something like this. If you look, these have a common denominator, so I can actually combine them. So I'm going to put it cosine x minus 1, or not minus 1, needs to be times 1. Oops, sorry. So just be negative cosine all over sine x, sine squared x. And this guy is still plus 1, sine squared x. Since they have the same denominator, that's where I was going earlier, is 1 minus cosine x all over sine squared x. So it's the same. It didn't ask us to prove it, but I think sometimes that's helpful. All right, so we've talked previously about these two concepts, that if I have a position function, the first derivative of the position is the same as velocity. So that's going to introduce us to something called the second derivative. Okay, acceleration is a second derivative of your position, first derivative of velocity. So one derivative takes you to velocity, the next derivative takes you to acceleration, which means it's done twice from position. Okay. Also, for higher orders, it looks like this. Things to notice would be, if you notice the tick marks go up until 3. So you have your third derivative, or y triple prime, with how you say it. But after that, it's just the fourth derivative. Okay. These sets will be the things you see most often. But these are all other notations. Keep in mind, this notation is asking you to take the derivative of something. It's like an operation. Okay, last example is a word problem. It says the moon has no atmosphere, falling object encounters no air resistance. Therefore, a hammer and feather would fall at the same rate, meaning that it has the same speed. Okay, the position function is given by this s of t equals negative 0.81 t squared plus 2. Its height in meters, and t is time in seconds. That's kind of important, as shown in the figure to the right. What is the ratio of the gravitational force to the moon? So gravitational force in this case would be a type of acceleration. And so gravitational force on Earth, we have previously learned, if you're doing the meters per second, is negative 9.8 meters squared per second. Okay, so that's what we're going to compare. So there's that. And so what we first need to do then is find the force on this object, which will be our acceleration. So our a of t is equal to v prime of t, which is s double prime of t. So before we can do that, I need to know my v so I can derive it. So if s is this, then v is the first derivative of that. So I'll multiply that 2 down, decrease the power, and I get this. So then if I derive that, I actually get my acceleration, which would be the second derivative of my position, and I would get negative 1.62. Okay, and that would be meters squared per second. Again, the question, though, asks for your ratio. So I'll do my Earth, because it says Earth to moon. So Earth on top and moon on bottom. And you are going to get a positive number because you have negative over negative, and you will get a decimal. I don't know if I have a calculator. So we'll have 9.8 divided by 1.62, and you're going to get 6.04938. Take it to 5 decimal places. Because the AP test will grade you on that. All right, be looking for that homework assignment. It is posted, but it's not going to be due till next Friday.